Welcome to episode 55 of the Pulse of Physiology. I'm your host, Dr. Jim Davis, and today we're discussing pulmonary diffusion, the process by which oxygen and carbon dioxide move between alveoli and pulmonary capillaries. By the end of this episode, you'll understand how partial pressure gradients drive gas exchange, how factors like surface area and diffusion distance impact diffusion, and how local oxygen and carbon dioxide levels regulate blood flow and ventilation. So let's get started. Now, gas exchange in the lungs occurs because of differences in partial pressure between the alveoli and pulmonary capillaries. Oxygen and carbon dioxide move passively by diffusion, meaning there's no energy that's required, and they both follow their respective gradients. Oxygen will move from the alveoli to blood because the alveolar pressure of oxygen is about 104 millimeters of mercury, whereas the partial pressure of oxygen in venous blood is about 40 millimeters of mercury. So we've got quite a large gradient. Carbon dioxide, on the other hand, moves from the blood to the alveoli because the partial pressure of carbon dioxide in the veins is about 45, whereas the partial pressure of carbon dioxide in the alveoli is only about 40. Now, this pressure difference ensures that oxygen enters the bloodstream while carbon dioxide is expelled during exhalation. The rate of gas diffusion is influenced by something called Fick's law, which identifies multiple factors that affect diffusion, such as surface area, diffusion constant, pressure gradient, and thickness of the diffusion barrier. So with surface area, if you have more surface area, you're going to have faster diffusion. The diffusion constant is specific to each gas. So one of the things that's kind of important to know is that carbon dioxide actually diffuses more easily than oxygen. Larger gradients increase diffusion, and this is a common theme throughout this semester. And then thicker membranes result in slower diffusion. Basically, they have to go through more walls or a greater distance. So when it comes to pulmonary diffusion, if we're talking about surface area, we're talking about alveoli. So if we have more alveoli, we have more diffusion. So there are diseases like emphysema, which reduce surface area, which impairs oxygen uptake. Then there's partial pressure gradient. A larger difference in pressure means more diffusion. At high altitudes, atmospheric pressure of oxygen is lower than at sea level, which reduces the alveolar venous oxygen gradient, which makes oxygen diffusion less efficient. And then finally, there's membrane thickness. If we increase the thickness of the alveolar capillary membrane, such as what happens in pneumonia or pulmonary fibrosis, this reduces diffusion efficiency. Now, gas exchange is locally regulated by adjusting pulmonary flow and airway diameter in response to oxygen and carbon dioxide levels. Low alveolar oxygen results in pulmonary vasoconstriction. What this is doing is this is reducing pulmonary blood flow to poorly ventilated areas. In other words, you don't want to send blood to pick up oxygen where there's low levels of oxygen. High alveolar carbon dioxide causes bronchodilation, so that increases airflow to eliminate carbon dioxide. Whereas if you have low alveolar carbon dioxide, this results in bronchoconstriction. So we're reducing airflow to conserve carbon dioxide. As we've talked about in the previous podcast, carbon dioxide is used to regulate acid-base balance. Now, cellular respiration is where oxygen is consumed and carbon dioxide is produced. This is important for a variety of reasons, but one of the things that this does is this maintains the pressure gradients that are needed for diffusion. Increased metabolism, such as what happens during exercise, leads to lower venous oxygen, which increases oxygen diffusion into the bloodstream from the alveoli, and higher venous carbon dioxide, which makes it easier for carbon dioxide to diffuse from the bloodstream into the alveoli where we can breathe it out. So let's summarize with 4 key takeaways. Oxygen moves from the alveoli to the blood. Carbon dioxide moves from the blood to alveoli, following their partial pressure gradients. Fick's law, and just to be clear, you'll never have to calculate anything with Fick's law, explains how surface area, gradient size, and membrane thickness influence gas exchange efficiency. Pulmonary arterioles and bronchioles adjust to local oxygen and carbon dioxide levels to optimize gas exchange. And finally, increased metabolism increases oxygen uptake and carbon dioxide removal, which reinforces gas diffusion. And so that's it for episode 55. I hope this episode has helped clarify how pulmonary diffusion works and what factors affect it. Join me next time for episode 56, where we'll discuss ventilation-perfusion matching and its role in efficient gas exchange. Until then, keep questioning, keep exploring, and stay curious.